So we are on a tight ship, so I'm going to try to keep everyone on time. But our first speaker is Milad Abolhasani from NC State.
Great. Well, hello, everyone. I want to start with thanking the workshop organizers for organizing such an interesting and timely workshop. And for the next 18 minutes, I'm going to talk about some of the work we've been doing in my lab over the last 7.5, 8 years to integrate human knowledge, AI, and robotics to accelerate discovery of materials and molecules with what we call autonomous labs or self-driving labs. So why do we need to integrate all of these to accelerate discovery of materials and molecules? Well, most of the time when we're looking for a new material or molecule, we're dealing with this, what we call a chemical or material universe. Unfortunately, we don't have a map of this universe. If you do, please give me a copy. That would be definitely worth billions of dollars. But we don't have this map, so you're just randomly searching through this space using a Edisonian trial and error-based techniques. So that's 50% of the problem. The other 50% is the way we navigate this space is mainly using human knowledge. We send our highly trained scientists in the lab, spending 70, 80% of their time just doing repetitive tasks. At the end of the day, they go back to their computer, look at the data, 1, 10, 20 experiments they've done, and they use their intuition to decide what is the next experiment to do. So that's our traditional closed loop science. But it's very slow, resource intensive, and expensive. It takes 10 plus years to discover new material, catalyst, or molecule, or even scaling up processes. And it typically takes more than $100 million of R&D to come up with a new material, catalyst, or process. So there's a lot of time gap between that running an experiment, getting a data, and making a decision about what is the next experiment to do. So looking at this picture, there's a lot of room for improvement to accelerate that closed loop science. For example, we can leverage the recent advances in robotics, lab automation, and AI. So bring robotics and lab automation in the lab so we can have this end-to-end automated experimental workflow. And then use AI, machine learning, to model our reaction process system you're studying, and then more intelligently make a decision about what should be the next experiment to do. So we can close that time gap between running an experiment and making a decision about the next one. So this would be our modern closed-loop science. And in return, what you get out of these self-driving labs is a robotic co-pilot for human scientists. You're not taking the scientists out of the loop of discovery. You're just providing that robotic co-pilot so you can accelerate your navigation of that infinite chemical universe. And the potential here is that we can reduce that time to solution 100 to 1,000 times compared to the conventional methods of doing chemistry and material science. And by nature, these materials acceleration platforms are much more efficient, material efficient, so they reduce the carbon footprint of your discovery. And if you use scalable reactors, then you can also reduce the time from discovery from lab to market. Now, depending on how you bring robotics lab automation in the lab, how you integrate it with the humans, you can go from piecewise operation all the way to self-motivated autonomous labs. We are very far from self-motivated autonomous lab, that there's no human input. Maybe in the next 50, 100 years, we're going to have self-motivated labs. Whenever we have AGI, maybe we can think of self-motivated labs. But for now, where we are is this closed-loop autonomous labs, that the human scientist or the user still provides or defines a problem of interest, and then defines maybe the initial hypothesis. Then the self-driving lab takes that problem, define parameter space, and very rapidly, in a closed-loop format, navigates the chemical space. So you start with a human-defined problem. You can use materials informatics, cheminformatics, depending on if you're looking at a material problem or a chemical problem. And then you can down-select few target potential materials, catalysts, molecules. But those are still in the digital world. Those are predictions by your AI. So what does the self-driving lab do? Bridges that gap between that digital prediction and the physical reality. It takes the predictions and tests the synthesizability, refines the hypothesis, and at the end of the day, what you get out of the self-driving labs is that we can reduce that time to solution 100 to 1,000 times. And then the next question is, how do I build that ideal autonomous lab? So when you think about building an autonomous lab, the first thing that a chemist might do, they might go in the lab and just automate everything. So that's not the most efficient way of building an autonomous lab. That's an engineering question. That's an engineering problem. That's an opportunity for us to re-engineer the way we think about experiments. We have to think about material efficiency. That's our opportunity to reduce the chemical consumption when you think about building a new end-to-end automated experimental workflow. Then we have to think about precision and reproducibility of the automation. So we all think automated solutions are very precise and reproducible. They're absolutely not precise and reproducible. You have to spend a lot of time making sure your automated solution is precise and reproducible. Even liquid handling, you start dispensing viscous solutions, then your precision and reproducibility decreases significantly. Then we have to think about in situ online characterization, how you integrate these with your reactors. And at the end of the day, what we want to generate is that big reliable experimental data. But you have to also, again, thinking about reproducibility and data transfer, we have to learn how we can actually transfer data between different labs. When you have a lab that's using batch reactors and another lab using flow reactors, completely different reaction dynamics, different reactor geometries, different mass transfer, heat transfers. How do we transfer the data between these different labs studying the same problem? So in my lab, thinking about big experimental data and reliability, reproducibility of experiments, instead of running reactions in batch, if you have a solution phase reaction that can be catalysis or material synthesis, instead of using batch reactors that come with inherent problems like large chemical consumption, uncontrolled heat and mass transfer rates, or very long delay times in startup and shutdown of reactions, especially when you're doing high pressure, high temperature reactions. Instead of batch, we go with flow, and we run reactions in flow reactors. Flow chemistry and microfluidics has been around. They have been around for more than 30 years. So we've not come up with microfluidics, but we're using it as the reactor of choice for our self-driving labs. Because what we want to do is to provide this big, reliable experimental data for the AI agent of our self-driving labs, so we can have faster turnarounds in deciding what should be the next experiment to run. So I'm not going to highlight all the advantages of microfluidics. What I want to highlight here is that enhanced heat mass transfer rates and photon flux. So if you have a reaction that's heat, mass, or photon flux limited in batch, you run it in flow, you can go from hours and days of reaction times to few minutes. So that process intensification is absolutely important to provide, again, that big experimental data for the AI agent of your self-driving labs. And then that ease of integration with analytical tools. We can integrate spectroscopy, chromatography tools with these flow reactors. So intensification and miniaturization and reliability, reproducibility of the data that you generate are the most important reasons that we use flow chemistry as the reactor choice for our self-driving labs. So in my lab, we basically designed these bespoke flow reactors. We integrate them with robotic solutions. This is liquid solid handling robotics to automatically prepare the stock solutions of the reactions that go into our flow reactors. We develop our bespoke in situ or online characterization tools to automatically characterize the product that comes out of the reactor. Now we can do photocatalysis, we can do just homogeneous catalysis or heterogeneous catalysis, or we can synthesize inorganic materials or different types of nanoparticles. It doesn't matter what the application is, the idea is the same. And then we use AI agents to model the reaction and process that we're studying, and then decide what should be the next experiment. Again, what I want to highlight is the role of that human user defining the problem, defining that initial hypothesis. And then we use these autonomous labs as our foundational technology, and then we apply to two areas, nanoscience and catalysis. And the third research area, my lab, we use all the data machine learning models that we develop for nanoscience and catalysis to better understand the underlying mechanisms of the processes we study. So I mentioned robotics. So this is an example of one of the robotic solutions we use to automatically prepare the stock solution of reactions. Here we're using solid dispensing, liquid dispensing under inert environment in a customized triple glove box. So we can automatically prepare the stock solution of any reaction that we're interested to explore. This can be, again, homogeneous, heterogeneous catalysis under inert environment, so we can work with air and moisture sensitive chemicals. And then we can do initial solubility screening, heating, shaking, and we can even do initial parallel batch screening to find out some potential hits that then we can take those and run them in our flow reactors. And then we use both mobile and stationary robots for sample transfer. So whenever we do reactions in parallel and we want to do some ex situ automated characterization, we use mobile robots to transfer the samples. And if the characterization unit can be integrated next to our synthesis robot station, then we just use those stationary robots. But as I said, the core of our self-driving labs are flow reactors. That's where we take advantage of process intensification to rapidly synthesize materials and molecules at a rate of recent throughputs can be in the order of even hundreds of experiments per minute. And as I said, we've been working on these self-driving labs for the past 8 years. These are just some examples of these self-driving labs that we've built. So for the next 8 minutes. I'm going to show you some examples of these, maybe 2 examples of nanoscience, 1 example in catalysis. So in the hardware design, we focus a lot on the modularity of these flow reactors. We want to make sure that the hardware is as modular and flexible. So we have flexible automation we can apply to different types of nanomaterials. We can do core nanoparticles, we can do core shell, and so on. So we automatically prepare the stock solution using the robotic platform that I showed you. And then we automatically feed those to our pumps. We can continuously deliver the precursors into our flow reactors. They get mixed. They flow along that tube. That's where the reaction happens for a specific reaction time at a specific temperature. At the end of the reactor, we have that in situ diagnostic tool. We do spectroscopy or chromatography. You can do mass spec. We have IR, NMR, and so on. You can characterize your product. So in this case, this is for optically active nanoparticles. So you can do in situ UV-Vis, near-infrared absorption, or fluorescence spectroscopy. If you're doing organic synthesis, you can do in situ flow IR, or you can do online HPLC, GC, mass spec, NMR, and so on. Here's an example of synthesizing optically active nanoparticles. These are quantum dots we're synthesizing in a flow reactor. And that's an example of a fiber coupled spectrometer that allows us to monitor the optical properties of these nanoparticles synthesized in flow. And then we have those mobile flow cells that move along the reactor, so we can have access to different reaction times along the reactor. And then we can have access to reaction times in the order of milliseconds. We can also do photocatalysis in these reactors. So this is an example of intensified, very materially efficient flow reactor doing photocatalysis in a 4 microliter droplet and going from reaction times of 48 hours to 20 minutes in a flow reactor. So this photocatalysis is actually doing band gap tuning of these ionic semiconductor nanocrystals under collimated UV light. And then that's a picture of the experimental setup. And we can monitor the reaction in situ just doing a spectroscopy. Here's another example of doing photocatalysis in flow. This is heterogeneous catalysis pack bed using titanium and rhodium. This is for room temperature hydrogen release using, or continuous room temperature hydrogen release using a liquid organic hydrogen carrier. And we've shown that with flow chemistry, photocatalysis, and precision engineering of the photocatalysis, you can actually intensify or accelerate that hydrogen recovery by 100 times compared to batch reactors. So that's automated flow. That's just a hardware of that self-driving lab. Now you get to that decision-making part, the way you can actually use AI to decide what should be the next experiment. So you leverage the high-throughput nature of these flow reactors to use all of the in situ and in the lab, in-house generated experimental data. These are our ground truth experimental data that we're generating in the lab to train a predictive machine learning model. This is, for example, Bayesian optimization framework. And then you use, for example, an ensemble neural net to generate the uncertainty of your prediction, and then you use decision-making on the uncertainty with uncertainty quantification to automatically decide what should be your next experiment. So uncertainty quantification here becomes extremely important. Depending on the objective function or the goal of your autonomous campaign, you might be doing exploration, exploitation, or balance of those two. And then the next question is, so what is the most efficient AI agent that I can use for this autonomous experimentation? There are hundreds of different machine learning modeling techniques, decision-making policies, different uncertainty quantification techniques to screen all of those parameters and optimize the AI agent of our self-driving lab. Again, we leverage the high throughput screen nature of these flow reactors. We train a digital twin on the process itself, and then we do a lot of visual screening, hyperparameter tuning of the AI agent before we integrate with the hardware of our self-driving lab to do our autonomous campaigns. And then we integrate the fine-tune AI agent with our hardware, and then we can run autonomous campaigns, discovering the most optimal synthetic route of, for example, synthesizing optically active semiconductor materials. We can then switch from discovery mode to continuous manufacturing. We've shown we can do 11 input, 2 outputs within 90 minutes. This is a multi-step synthesis example. And this one has 9 inputs, high pressure, high temperature synthesis of inorganic semiconductor material. This one goes up to 300 degrees Celsius, and we can heat and cool them at 400 degrees Celsius per second, run it up at 2000 PSI pressure. And instead of just doing optimization and just showing that we can actually learn something within something that we already know, in this example, we discovered the best-in-class optically active nanoparticle for applications in photovoltaic devices. Here's an example of the reactor in operation, 300 degrees Celsius, 0.5 milliliter scale reactor, continuously synthesizing these these materials. They've also done multi-step chemistry. This is core shell nanoparticles with 40 different input parameters, 40 different input parameters. It's a very large reaction space. They've done it in 4 microliter scale droplet. It took us about 3 years to build the hardware and automate everything. And then we use reinforcement learning to explore this high-dimensional space, core shell nanoparticle synthesis. I'm not going to go into details of this, but within 1 month of autonomous experimentation, this, they call it AlphaFlow, AlphaFlow platform discovered a new chemistry, a new way of making these core shell nanoparticles that outperform just human discovered fine-tuned chemistry of the same core shell nanoparticles over 15 years of academic literature. So this is an example of human knowledge, prior knowledge. Those precursors that we provided for this chemistry, those are all prior knowledge. That's human knowledge plus robotics, lab automation, AI, outperforming humans only. So it's an example of how when you collaborate with AI robotics, you can actually outperform just humans only. Now, for the catalysis part, I only have 2 minutes, but for the catalysis part, we basically took the same idea and we wanted to see if we can autonomously map the performance of a new catalyst, new ligand for homogeneous catalytic applications. And when you do catalysis, and for example, you have a transition metal catalyst, it's homogeneous catalysis. Now, this workshop is for heterogeneous, but the same rules apply, the same tools here apply for heterogeneous catalysis as well. Then you get your yield and reduce selectivity of your product. Now, depending on what ligand you have, the structure of the ligand, the reaction conditions, you're going to get different selectivity and yield. And if you do high throughput screening or just manual experimentation, this is what you're going to get. The white dots are just your experimental data within what is possible with that catalyst. The red points are your Pareto optimal points. What you want to do is to find only those red dots. Those are your Pareto optimal points of your yield and selectivity. And you want to do it very quickly so that you can benchmark different catalysts, different ligands, and then that you can feed that to your catalyst discovery workflow. So what we did, we developed this self-driving catalysis lab using the same concept that I showed you, flow chemistry. In this case, we are doing high pressure, high temperature gas liquid reactions using rhodium catalyzed hydroformylation of olefins as our test bed. And we use Bayesian optimization also for this example. But the only difference between this and the nanoparticle case that I showed you, instead of just doing optimization of single or multiple objectives, in this case, we are doing Pareto mapping using an expected hypervolume improvement policy, basically simulating the future experiments, looking at which one has the highest potential of pushing that Pareto front. And then we did the same fine-tuning of the hyperparameters of the AI agent of this self-driving lab using digital twin that we trained our in-house generated experimental data. I'm going to skip all of those. This is an example of the experimental performance of this self-driving catalysis lab. We call this one FastCat. And within 30 autonomous experimentation, you actually found the ground truth experimental Pareto front of selectivity and yield for a given ligand for this hydroformylation of olefins. Then we tested different ligands. Again, everything autonomous, no human intervention during that Pareto front mapping. And what we did, we actually spent a lot of time to benchmark the performance of our small-scale flow reactor against that industrial-scale batch reactor. And we reverse engineered design of our flow reactors so knowledge can be scalable. And then once you do that, then the result that you get out of your autonomous lab can be directly transferred to industry. And these are just 2 examples of the conditions ligand selected by autonomous lab transferred to a larger scale industrial reactor. So what is the future? So what I showed you was just some snapshot as to what is possible when you integrate human knowledge, lab automation, AI. So thinking about the future of these self-driving labs, they become extremely powerful when you can have a network of distributed autonomous labs, not just in facilities, but actually in every single lab. But then the question becomes, how do you transfer knowledge between different labs? How do you transfer knowledge between different robots with different hardware, different reactor dynamics? So then you start thinking about the abstraction and how much abstraction is needed. There are a lot of open questions that we have to answer, but when we are building these autonomous labs, you have to think about benchmarking experiments. So definitely encourage the whole community to come up with or run these very simple benchmarking tests so that you can do apple-to-apple comparison. And then, yes, reproducibility and abstraction, extremely important. So hope I was able to convince you that autonomous labs can help us close a time and a scale gap in discovery and development of new materials, molecules, and processes. At the end, I want to thank all my group members who did all the work I presented today and our funding agencies and collaborators. Thank you all for listening. I'll be happy to take maybe one question.
I have one quick question while we switch the computers.
Or maybe after the session.
What you are doing in your lab is future for us.
But the session is called Future Labs.